Section 2.3 is method 3 for solving first order differential equation, which is called exact differential equation. Now, we're going to see what is exact differential equation and how to solve it. But before we see that, really, we have to talk about partial derivative, because it's going to be needed. Partial differentiation, we're going to need it in section 2.3 and section 2.4. Now, what is partial derivative? So consider this function. This function, it can be seen as y function of x, and in this case, to differentiate, you have to say 3y square y prime. You have to do implicit differentiation, which you do in calculus 1, and then you have to rearrange and put y prime on one side, and you are going to end up with the derivative. This is one full page. Or it can be seen as f function of x and y. So really in this case, x and y are both independent variable, while in this case y is a function and x is independent variable. Now if we look at it this way, as a function of two variables, in order to differentiate, we talk about partial differentiation. So we can do partial derivative with respect of x, and partial derivative with respect of x means we differentiate with respect of x, we assuming y constant. For example, if we want to differentiate this with respect of x, then derivative of this part is equal to 0 because it's y only, it's a constant. Derivative of this part, y squared is constant. So it's like you are differentiating 6x, so you say 6. So y squared x derivative is y squared. Derivative of this with respect of x, y squared is constant, so derivative of x squared is 2x, so it's going to be 2xy squared. This is partial derivative with respect of x. Partial derivative with respect of y, which is this, we can do partial differentiation with respect of y. In that case, we assume x is constant, so derivative of this is equal to 3y squared. Derivative of this, x is constant, so 2yx, which is this, and derivative of that, x squared is constant, so 2yx squared. This is partial differentiation. We say partial differentiation when we have a function of more than one variable. We can also talk about second derivative. You can differentiate this again with respect of y and this again with respect of x, so you are finding second partial derivative. We say this is mixed partial derivative. If you differentiate this with respect of y, then you assume x constant, so this will be 4xy, and this will be with respect of y 2y. And if you differentiate this again with respect of x, this is going to be 0 because there is no x, and this will be 2y is constant, so x squared, derivative of x squared is 2x, so it will be 4xy, and derivative of this with respect of x is 2y. Now, there is a very interesting thing here which you can observe, that the mixed partial derivatives are equal, which means it does not matter which one you start to a differentiation, x and then y, or y and then x, the second derivatives are equal. This is a very interesting fact which we are going to need later on when we talk about exact differential equation. Before we start and say what is exact differential equation, there is a very interesting fact here which we must say. As you see, to differentiate this function now, we have the choice by assuming y function of x, and like I said, we do one full page and say 3y squared y prime in order to find dy dx. And instead of that, now knowing partial differentiation, you can assume this is function of x and y, and then if you find partial f, partial x, which is this one, and write dx, plus partial f, partial y, and you write dy, you are going to get dy dx, which is similar to this, the same answer, but in one step. So if you use partial differentiation, this is partial f partial x, and this is partial f partial y, you will be able to find dy dx in one step. Now, we are ready now to talk about what is exact differential equation. Exact differential equation is of this form. This is actually exact differential equation. The reason it is exact, because it is partial f partial x plus partial f, the same f, partial y. So it is exactly total partial derivative of the same function. And so we say this is exact. Now we know this is exact now because we have f. Okay, so now this is the meaning of exactness. Exactness means that the differential equation is total of partial derivative of the same f. How can I check if this equation was given to us? How can I check it is exact? How can I check it belongs to one f and it is total of partial f partial x partial f partial y? Because in reality f will not be given. F is the solution. Only differential equation will be given. So how can I make sure, or how can I check it is exact? We can check exactness simply by differentiating again. Because we have said before that the partial derivative of a function, the mixed partial derivative of a functions are equal. So to check exactness of this, to check that it is belong to one f, which is like this, differentiate again. If you differentiate this again with respect of y, which is 2y plus 4xy, and differentiate again this with respect of x, so it is 4xy plus this is 0 plus 2y. If they are equal, that means it was belong to 1f, because what we are finding here is the second derivative. So this is what I wrote here. I said equation 2, which is this, is called exact differential equation because it defines exactly total of two partial derivatives of the same function f from equation 1. Now, we can check exactness by using the mixed derivatives. If we differentiate again, then we are finding the mixed derivative. If they are equal, then it is belong to 1f. So I will repeat myself here and say what is exact differential equation and how can I check that the differential equation is exact in general. An exact differential equation, it has to be of this form, where right hand side is equal to 0 and the left side it has to be dx dy, and if m is partial f partial x and n is partial f partial y, so it's belongs, so this is of this form, which is partial f, then we say it is, this is the meaning of this is exact differential equation. How can I check that a given differential equation is of this form? We can check by differentiating m. If we differentiate m with respect of y and n with respect of x, if they are equal, then we say it is exact. Because when you find derivative of m with respect of y, that means you are differentiating or you are finding second derivative of f xy. And when you differentiate this, which is this, with respect of y, so you are finding actually second derivative of f with respect of yx. If they are equal, then the differential equation is exact. So you have to differentiate m with respect of y and n with respect of x, which are these. If they are equal, differential equation is said to be exact. Now we have already seen what is exact differential equation and how to check if a differential equation is exact. Now how do we solve an exact differential equation? So we are back now to the first page. That was our first differential equation, which we know it's exact because we had f, which is the solution actually. We know this is partial f, partial x, because we have f. So it's exact because it's belong to, this is partial y. So it's belong to 1f. Now, if that was given to us, and we said solve, so solution is not given, f is not given. How do we check exactness and how do we solve? We have seen how to check exactness, so we should start like this, the solution. First of all, it has to be written in this form. Right hand side is 0, this is dx and dy. So we are going to call this function mxy and this function nxy. We should start by checking exactness. My is 2y. We have already seen how to check exactness before. And nx, which is 4xy plus 2y. Since my is equal to nx, so we say differential equation is exact. Now, how can I solve? Exact means we have partial f partial x and partial f partial y in the differential equation, and we are looking for f. That's the solution. So we can find f by integrating this or integrating that. We have to choose the easiest. Here both are easy, so I'm going to integrate one of them only. Later on in the next example I will integrate both to show you the different ways. Anyway, so we are going to find f by integrating m, which is y square plus 2xy square dx. With respect of x, integration, so simply you are putting an integration here. With respect of x, so this is constant, so you are like integrating 6, which is 6x, so you are going to say y square x. With respect of x here, y square is constant, this is constant, so you are integrating x, which is x square over 2, 2 cancel with 2, so you are going to have this. Plus constant, now constant is not a number now because we have assumed y is constant, so a constant can be something with y. So let's call it g of y or any function of y. So this is the f. So really if you compare this f with here, we have already found this and this. We just have to find y cubed, which is the function of y, and it is missing here. We have used partial f partial x to find f. I'm going to use partial f partial y to find g of y in the following way. You differentiate your answer, which is f, and you compare it with n, because n is partial f partial y. Partial f partial y from here is equal to 2y x plus 2x square y plus g prime y. Compare it with n, and n is 2x square y plus a 3y square plus 2xy. You see 2xy is equal to 2xy here, 2x square y is 2x square y, so g prime y is equal to 3y square. So g of y is integration of 3y square with respect of y, which is y cubed plus c. So you can write back the function, which is the solution x plus x square y plus y cubed. This is actually, if you go back to here, this is what we have there. This is what we found. We have found all of this. But this actually is integration of 0. You see, when we use exactness, we were working on this side only. Integration of this side is f. Integration of 0 is constant. So the final answer anyway has to be written. So your final answer has to be written like that, which is y square x, which is f. You write f again. Okay, equal to constant. No need to write this constant because it will go on the right with the integration of 0. The integration of this 0 is this constant. Now let us see the solution procedure of exact differential equation using exercise 6. So I'm going to repeat myself here. Now this differential equation is not separable, it is not homogeneous because the degrees of the terms are not the same. So we have to check exactness. To check exactness, the differential equation must be written like this. Right hand side is 0 and we should have some function dx plus another function dy. Now to check exactness, we have to call this one m and this one, we don't have to call them n and m, but I mean we could choose any name, but we are going to call them m and n. Then we have to differentiate the first one, which is dx with respect of y. So x is constant now. So this is constant, derivative of this is 2yx, and derivative of this is 1. And then differentiate this one with respect of x. So y is constant, so 2xy plus 1. They are equal, so differential equation is exact. Exact means that the differential equation now is of this form. This is partial f, partial x, and this is partial f, partial y. This is the meaning of exactness. So we have two derivatives of f now, and we are interested in finding f, which is the solution. So we can either integrate this or that. We have to choose the easiest. Now, I have written it here, or it's written here, using both integration. Okay, to let you see the method. Either you do this or that. So if you choose to integrate, because here both are easy. So if you choose to integrate m, which is the first part, so integration of xy squared plus y dx, y is constant, so y squared will remain x squared over 2 plus yx plus g of y. When you are integrating with respect of x, y is constant. To find g of y, you have used partial f partial x. Now you have to use partial f partial y to find g of y. How? You have f. So differentiate f with respect of f and compare it with n. Okay, you can, because they are the same thing. Because n, this is n, is partial f partial y. So partial f partial y from the answer is equal to 2yx square over 2, so yx square plus x plus g prime y equal to n upon the equation, which is this. This is equal to this, that's equal to that, so g prime y is 0, so g of y integration of 0 is constant. Then you go back and write what is f. And the solution is written as f equal to constant. And instead of that, you could integrate n. So if you integrate n, it's the same thing, but you have to say, when you integrate n with respect of y, dy, so x is constant, so you don't say plus constant, you say plus g of x. So when it's dy, you say plus g of x. This is f, and you have used n. You are going to use now m, which is this, which is partial f partial x. So now you are going to find partial f partial x from your answer and compare it with m, because m is partial f partial x. Partial f partial x from here is this, equal to m from the differential equation. Compare them. You see, at this step you should be able to check your solution, because you must have similarities between the terms, and g prime x must be a function of x only, or a 0 or a constant, and the g prime y must be a function of y only, or a 0 or a constant. G prime x here is 0, so g of x is constant. Then you write back your answer, and your final answer will be equal to C.